All right, so today we're talking about these things called optimization problems. They're a special little class of word problems that you see in calculus. So that's our topic. We're only going to spend one day on it. Really, the calculus behind these is very simple. The problem is the pre-calculus. Can you read a word problem and write a formula out of that? And also, can you solve systems of equations and stuff like that when they have fractions in them? So I think that's where most of your guys' hang-ups are going to be probably, is going to be where you have to write the formula and solve the equations out. It's not going to be the calculus. The calculus is pretty easy. So that's our topic. So today's our last lesson. Tomorrow we have off. Thursday is going to be a short day, but we're going to do an in-class study session that day. Friday is Unit 5 test. And then next week on Monday, do we have Monday? No. All right, so then Tuesday we'll finish our test with the review portion and the FRQ, and then we'll move on to Unit 6. We are running out of time, I'll tell you that. All right, so what is an optimization problem? Basically, it's just where you try to find the best or the worst in a particular scenario. So I've got a word problem down here. It says you have 100 feet of fencing, and you want to make a rectangular region. How should you arrange the fencing to cover the greatest possible area? Okay, so that's like an example. And there's all kinds of ways you can set that up, but one would give you the most area, right? And that's what we're looking for, is what setup would work the best. Why is that important? Because in the real world, they do that all the time. You know, if you want to design something and waste as little material as possible, or when you're talking about, you know, making money, you want to maximize profit or minimize costs. These are all examples of where that would be useful. So I've got some steps here that we're going to follow. You're going to write a primary equation. You're going to write a secondary equation. And so since you have two equations, basically after that, you're going to solve a system of equations. At some point, though, we're gonna find the minimum or maximum. So let me go into a little bit more detail about what this primary secondary equation thing is. The primary equation is the one you want to minimize. So up here in this sample word problem I gave you, what are we trying to find the greatest of? The area. So the formula for an area, you know, we're going to turn that into an equation. That's the one we're going to try to find the maximum of. Now you guys already know how to find maxes and mins, right? We take the derivative, set it equal to 0, and that's how you find your maxes and mins, right? So that's what we're doing. That's the calculus part of today. Now the secondary equation is a constraint that's being put on your word problem. So in this word problem up here that I read to you, the constraint is they're only letting you have 100 feet of fencing. So that's going to be a secondary equation that we're going to have to set up that's going to restrict our possibilities for the area. All right. That's basically it, though. Once you have that all set up, you're going to end up taking the derivative, setting it equals 0, and that's going to help you find your min and max. You always want to make sure that your answers work at the end. We'll probably come across one problem today where it's like, you get an answer that seems to work, but then you plug it back and you find, oh, that's bogus, it doesn't work. Word problems are like that because math has an infinite range of possibilities, but word problems in real life sometimes restrict you. So we always got to go back and check our answers to make sure that they're reasonable. Another thing you want to make sure is that you're answering the question they're asking for. You know, it's one thing if I ask you what's the maximum area. It's another thing if I'm asking you what side lengths of this fencing is he asking for, right? So it's different questions. So you got to read that carefully. So some common types of problems involve area, volume, distance, and shapes inside of other shapes. Those are really common types of questions. So I have all kinds of them. We'll probably only get through 3 today. And then what I'm going to do is once you guys go home is I'll do a few more examples for you guys to look at. So your homework for tonight is twofold. You're going to look and watch a few more examples just for homework. And then you're going to pick 5 problems from the worksheet that I pass around. It doesn't matter to me what 5 you choose to do. I don't know if it's still out there or not. But the homework worksheet, I put, I'm only going to do 5. You can pick any 5 you want to. So that is that. So we're doing optimization. Like I said, I don't feel too bad about only getting through 3 and having you watch videos on the rest, because like I said, really most of the struggle is not going to be the calculus. It's just going to be setting up the formulas and solving the equations, which is all pre-calculus stuff. So what we'll do is we'll start off with an easy one. I printed these out for you, so if you look at the back of your notes, they're already printed. We're going to do number 1 first. So let's read it. A cryptography expert is deciphering a computer code. To do this, the expert needs to minimize the product of a positive rational number and a negative rational number. Given that the positive number is exactly 6 greater than the negative number, what final product is the expert looking for? It's a lot of words going on there, so I'll try to make sense of this. We have a positive number, we've got a negative number, and they have to be 6 spaces apart. And we're looking for which numbers that when we multiply it give us the smallest outcome. That's what we're looking for. Now you might think, oh, we'll just test numbers, right? But this is rational, so they could be fractions. They could be any number of fractions. So we're going to go ahead and solve this using the process at hand. So here we go. So the first thing I gave you guys on your steps was to find a primary equation. Now, the primary equation is the one that you're trying to minimize or maximize. In this case, what are we trying to minimize or maximize? The product. So my primary equation is what I'm trying to minimize or maximize. And I'm trying to minimize or maximize the product of 2 numbers, and I don't know what they are. Okay, I'll let P be product, and I'll let X and Y be the 2 numbers. And I know that that's the one I'm trying to minimize or maximize, right? All right, now we have a secondary equation. The secondary equation is where they give you an extra constraint, so it can't be just any 2 numbers. What did they tell us about these 2 numbers? One of them is 6 more than the other. So don't shout it out, but see if you can write a secondary equation where one of my numbers is 6 more than the other. See if you can write that out. Anybody got an idea? Go to Princess. Sure. So X equals Y plus 6. Now I don't want anybody to shout it out. Once again, I want you to think, and I don't want shouting out because I want people to be able to think about it. Which one of these then would have to be the positive number and which one would have to be the negative number? So think about that for a second. It's good to know what your variables represent. What do you think, Tyler? Which one's the positive one? X is the positive? I agree. It has to be the bigger one because the positive number is, yeah, 6 more than the negative. Right? If this is 6 more than that, so the X has to be the bigger one, which means 6 has to, or X has to be the positive. So it's kind of good to know what your variables represent. So we have P, which represents their product. We have X, which is the positive number. We have Y, which is the negative number. All right, now we're ready for that next step. Oh, here's the homework. I'll pass that on. The next step I wrote says, it's a mouthful of stuff there. Solve for one of the variables in the secondary equation and substitute it into the primary equation so that your primary has only one variable. So I don't need to solve for a variable here, right? I've already got X solved for. So now it says after you solve for it, plug that into your other one. So I'm going to replace what variable? With Y plus 6. And that way, it's the same equation. It's just that now I have an equation with just one variable instead of 2 in it. So here's my function for the product. the product is y squared plus 6y. And I want to find the lowest possible product. In other words, I want to find the minimum of that function. How do you find a minimum? Yeah, what we've been doing all along, right? You find the derivative, set it equals 0, and where it equals 0, that would be a minimum or a maximum, right? So, solve for y, and we get -3. And that's my negative number, right? All right. So now, we want to also find the y value, right? So how do I find the y value? I'm sorry, the x value. Sorry. Yeah. So you're going to plug it into one of these up top. Now, it does matter which one, because this one has too many variables. If you plugged in a y here, you're going to have 2 variables left, right? But if you plug it in here, then you can solve for x, right? So you're going to usually use the secondary equation for that. So we have x equals, was it 6 plus y? Or is y plus 6? It's the same thing, but. And x is 3. So there's my x, there's my y. Now those aren't my answers. This is a good example of where you want to make sure your answer makes sense, because the thing here says what's the smallest possible product, right? That's not the product. Those are the numbers that I'm multiplying, right? So P is equal to x times y. We just found out that x is 3, y is -3, so the smallest possible product is -9. Okay. So we just found 2 rational numbers that are 6 spaces apart, such that one's positive, one's negative, and that's the smallest possible product you could get out of 2 numbers like that. Okay. So the calculus part is step 4, where you take the derivative set equals 0. The rest of it's all just algebra. So, do you guys want to try one like this? It would be literally the same question, but I would just change it from being 6 numbers apart to like 5 numbers apart. Do you guys want to try one? Hands up for if you want to try one like that. 1, 2, 3, 4, 5, 6. How many of you guys want us to move on and see a different type of problem? It's a tie. Tell you what, let's do another example, and we'll let you practice that one. Okay? Because that's what 5th period did. And I feel like that math is probably a little bit more that would be beneficial for you to practice with. But that's probably my easiest one I have to share with you. And I like to start there because it just kind of gets used to the steps. Primary, secondary, substitute, minimize. You know. All right, let's go ahead and do another one. I want to do number 2 off of that worksheet now. Go ahead and read number 2 really quick. I want you guys to read number 2, but to yourself, and then I want you to see if you could draw a picture. Read number 2 and see if you could draw the picture. We have these 2 pins that are side by side, right? And they share one side. All right, so at this point, we have x here, and here and here. All those are going to be the same, right? And then we have y here and here, and also on the bottom. So now I'm going to begin our steps here. I'm going to let you guys start trying to walk me through this a little bit. We're going to primary equation, you guys. So primary equation is the one you're trying to minimize. So what are we trying to minimize or maximize here?
It's just light up my day.
So. Read it again. What does it say we're trying to minimize or maximize? Area. Area. We're trying to maximize the area. So I want you guys to write for me a formula for the area. So for those of you guys that just walked in, we talked about. Very good. So my base is 2y, and my height is x. It's a rectangle, right? So it's base times height. Okay, now there is a secondary equation. This one's a little bit trickier. My last block got it, but only after a lot of leading questions. I won't throw you out there too much without any information. So the secondary equations, they're telling you that you're allowed to have how much fencing?
400 feet.
400 feet worth of fencing. So see if you could turn that into a secondary equation. I'll give you a second. It's the fencing, right? There's 400 feet. Each one of these is a piece of that fencing. So we have 3 x's and we have 4 y's.
I was
So
thinking it was all one big thing and not 2 things.
okay.
Because I forgot it's 2.
Okay. Yeah. Oh, I see. I see what you're saying. Okay. Yeah, so that middle piece, basically. So yeah, so there's our secondary equation. Now we do need to get a variable by itself, so let's go ahead and do that. I'm going to choose to get the y by itself. So y equals 100 minus 3/4 x. And now what do I do? Plug it into your primary, right? So I'm going to replace what letter? There we go. And now I'm just simplifying this a little bit. And that's the end of step 3. I bet you guys can finish it from here. All right, so what's up? Now what do we do? Kind of. Find the derivative, set it equal to 0, right? So, because we're looking for the minimum or maximum, if you multiply here, you get 6 over 2, which is 3. And then we set it equal to 0. Solving for x, we get x equals 200 over 3. Now what do we do? Plug it into which one? Secondary. Secondary. That's not the OG. I wrote that wrong. Okay, so these cancel. 4 goes into 250 times. And y is 50. So now what was the question asking for? Was it asking for... It's asking for the largest area? You sure? It's not what they told me last block. What's it asking for? What should the side lengths be, right? Now, and a subtle thing is, so when I first saw that, so how should they put it together? What should go here then? How many feet? 200 over 3 in here? 50. Now, they could have asked this question in 2 ways. They could have said, how big should the whole thing be? That would be 200 by 100, but they didn't say it that way. They said, how big is each corral? So it's 50 by 203. So our answers are 50 and 203. So this is, like I said, once again, they could be asking for different things. You just got to pay attention to what they're actually asking for. But there it is. All right, so why don't we let you guys try one like this? It'll be pretty much the same thing, but just with some different numbers. Sound good? And I think this is good because it gets you used to the process and also just the algebra of it all. It's not really to help you with the calculus because that part's step 4 and it's pretty simple every time. Just derivative equals 0 and you're good. The rest of it is really what you need help with. Setting up the formulas is the real killer, but the only way I can help you with that is by showing you as many different kinds of problems as possible. Okay, so why don't you guys go ahead and quietly read to yourself number 4 really quick.
Something that isn't.
All right, so a supermarket employee wants to construct an open top box from a 16 by 30 inch piece of cardboard. Big rectangle, right? To do this, it's going to cut out squares from each of the 4 corners so that the sides can be bent up, and that's going to create a box. Now, for those of you guys that have trouble visualizing that, I have constructed one here, but it's not 16 by 30. You cut out these squares out of the corners here and fold those up. You see you get a box, right?
Yeah.
All right, so that's what they're saying. That's not how anybody really makes boxes, but we're going to pretend that's how they make boxes for this word problem. So I'm going to give you guys a few pushes in the right direction, then I'll give you a sec to see if you can come up with the primary equation, okay? So first of all, we know that we're dealing with a giant sheet of cardboard that is 16 by 30. We also know that they're cutting out squares out of the corners. And do we know how long those are? No. That's what we're trying to figure out. So I'm going to let you guys see if you can come up with the primary equation. Go ahead. How can you tell what your primary equation is going to be? It's because you're looking for what you're trying to it's what you're trying to maximize or minimize.
Oh, yeah.
So what am I trying to maximize or minimize here? The volume. So we're looking for a volume of this box, right? How do you find the volume of a box? So there's your first push in the right. What does it say?
Okay, never mind.
Okay.
Never mind.
So how do you find the volume of a box, you guys? Length times width times height. Now that we're not going to have L, W, and H. You're going to put things in there. So I'll let you guys see if you can figure out what those are. I'll give you like another minute to see if you can figure out what the length. It kind of helps to see that little thing that I made. I don't know what I did with it. It's gone. I just had it in my hand and it's gone. Weird. Well, if you guys can imagine, this is what I'm actually looking at right here. This is what's left after we cut out those squares, right? Okay, so if I fold that up, what's the height of my box going to be? X. The X is the height of my box. Now my width, the cardboard used to be 30, but I took X off of both ends. So my width will now be 30 minus 2x. And my length will be the same thing. It used to be 16, but now it's minus 2x. Okay? So, after that, now this is another interesting thing. How many different variables do you guys see in this equation?
One.
Just one. I'm not counting the v. So, notice that we don't need a secondary equation this time to make it just one variable. This is one problem where that happens. Sometimes you don't need that. This box it has its own constraint built into it, so you don't need to do that. All right, so I'm going to skip a lot of the tedious stuff here just so you can get the main idea, and I'll bring this problem home at this point. So that what you would do here is you would FOIL this and distribute the x. Now if you did that, you would get 480x minus 92x squared plus 4x cubed. Then we take the derivative. Next, you look for something, we set it equal to 0, right? Now, just as a neat little trick, you don't have to do this, but it's a nice thing to be aware of. We could make this smaller by dividing everything by a common divisor, right? The biggest thing that I can divide into all three of these would be 4. So if I do that, I can get some smaller numbers. Now there's two ways you could solve this. You could either factor or do quadratic. I didn't want to try to factor that. I don't like factoring when the numbers are that big, so I used quadratic. But my students last block said they preferred factoring, so I'll go ahead and put that up. I believe you would get, see, 12 minus x times 10 minus 3x. And we get x equals 12 and x equals 10/3. Now something else that's happened here that's kind of new that we haven't seen yet is we got two answers. Now one of those is our answer. One of those is something that's going to give us the maximum possible volume. The other one is a bogus answer. And you can't really tell which it is just by looking here necessarily. Anybody got a guess about which one's probably bogus? Why 12? You're right. Good. So if you know that already, you're good. You couldn't take 12 off. Matter of fact, for the side that's 16, you couldn't possibly take 12 off both sides. But the real way you do it is just by plugging each one into the original equation and seeing which one actually makes sense. I'll go ahead and finish it. You guys can watch it if you want to. You're welcome to pack up and go. And like I said, I'll put more examples up for you to look at.
Who is still doing that? I don't know what's that. Kale, so we call it Kelly.
Bye. Alright, so go ahead and pause the video here and read over this really quick, make sure that you understand it. So our primary equation here, what we're trying to, in this case, maximize is profit. Profit is how much money you earn minus how much money it costs you. So they say that we're making this much for every phone that is sold. So that's going to be what we're earning. And that's for one phone, and we're selling that many phones. So you're going to multiply it by X. This is for each phone, this is how many phones we're selling. Minus the costs, and that's, it costs them $40 per phone, plus an additional $6,000 a day to keep this thing going. So we're not going to have a secondary equation. We're just going to go ahead and solve this as is. So the first thing I would do is distribute this x into the problem. This is going to be negative 0.05x squared. I'm going to rearrange these numbers too. Plus 110x minus 40x minus 6,000. And distribute the minus there. From there on out, the problem is going to be pretty much doable by you guys. Just getting it set up was kind of the issue, right? 110 take away 40, is that going to be 70x? Right? And we want to find the max of this function. So we're going to do p prime, which is going to be negative 0.1 x plus 70. Make that equal 0. And solving that, you get x equals 700, and that's how many phones they would have to sell in order to maximize their profit. So we only got one answer, so that has to be the answer. There's nothing else. Let's see, how many phones? Yeah, so it was asking for how many phones. This is the answer. If it asked us what the profit would be, then we would actually plug this back in and try to get the profit. But for now, we're good. All right, let's go ahead and take a look at another type of problem. Okay, this is an interesting one. We're looking for the point that's closest to the graph of y equals 7 minus x squared. So now this one's kind of tricky. My primary equation. Well, what am I trying to do? If I'm trying to find the point at which this point is closest to this point. Now, if we want to make a little graph of this, we could. It would look something like this. That's the graph. The point 0, 3 would be right about here. The question is, which point on this parabola is closest to this? We're looking to minimize this length right here. Now that's going to harken us back to some old geometry, maybe even some Algebra 1. But it's going to be the distance formula. We want to find the smallest distance between 2 points. So, just to refresh your guys' memories here, this is the distance formula. So I want to minimize that distance. I have 2 points. I have this point here, which is 0, 3, right? And then I have this other mystery point that I don't know yet. We'll just call that x and y. Okay? So we have d is equal to, my first x value we'll call x, minus x1, which is 0. And we have y2, which is going to be y minus 3. So I want to find the minimum distance between this point and this point using the distance formula. All right, so that's my primary. Now let's go ahead and take a look at my secondary. The secondary thing is the thing that limits what points I'm even allowed to have here, and that's this equation itself. It has to be points that are on this parabola. So my secondary equation is actually just that parabola. So that means that y equals 7 minus x squared. So I've already got y solved for, so if I just come back up here, x minus 0 is just x, so I'm going to have that as x squared. And then I'm going to replace this y with 7 minus x squared minus 3. And we're going to go ahead and continue simplifying this a little bit. 7 take away 3 is 4. All right. So now this piece here, I'm going to FOIL that out. That's going to be 4 minus x squared times 4 minus x squared, since it's being squared. If you FOIL that out, you're going to get 16 minus 8x squared plus x to the 4th. All right, so if we combine these two like terms, we have that. So now I've got my simplified primary equation. Now I want to find the minimum distance, so I want to minimize this. Now that requires me to find the derivative. Now we can find the derivative of this whole thing, but I'm going to show you guys a little trick here to kind of make our life a little bit easier. Taking the derivative of this is going to be a pain because it's a square root function. So, but here's the thing, don't you guys agree that as the inside gets smaller, so does the square root itself, right? So basically, if I can just find the minimum value of the inside, that's also going to be the minimum value of the square root. So what we can do is we can kind of create a D2 here, we'll call it, and I'm going to minimize this, which is going to give me my minimum values for the original function. So D prime, I'm going to call it D2 because it's not actually D, right? So the 16 goes away and up with negative 14x plus 4x cubed. Set that equal to 0. And now we can start solving it. So that would be a lot easier to find the minimum of than the square root function itself. You can still do it with the square root function, it's just that it's a lot more work. And so I'm just trying to show you guys how to take these problems, which are already kind of lengthy, and make them a little bit easier to do. Okay, so for this one, I would start by maybe factoring out a 2x, maybe even a negative 2x, which is going to leave me with 7 minus 2x squared. Okay, which means that I'm going to end up with two possible outcomes, either x equals 0, or if I solve this one, we're going to get a positive and negative square root of 7/2. And don't forget, it is a positive and negative. So I actually end up with 3 possibilities here. I've got 0, positive 7 root 2, and negative 7 root 2. Now it's only, well, maybe it's possible you can get more than one answer, but remember, we're looking for the point that's closest. Now, if you just kind of go back to our picture, it makes sense that we might end up with 2 answers. You know, you could have an answer over here and here that would both be closest to that point. So that really makes me think this is probably correct. This is another possibility, but you know, it could be equally far away, and so we actually have 3 points that are equidistant from the graph that are minimized. Or it could be that maybe this is actually one that's maximally far away from the graph, although I highly doubt that because I think the graph just gets longer and longer, so I'm pretty sure that's not it. But we'll find out. Let's go ahead and see what they are. Now, since the problem here told us that y equals 7 minus x squared, we're going to go ahead and plug in our answers. Now, if you plug in 0, we get 7. So 0, 7 is one of our possibilities. If we plug in negative square root of 7/2, we're going to get, I don't think I wrote that correctly. let's see, that's going to be 7 minus 7 halves. That's going to be 7 halves. So we would get negative square root of 7 halves, comma, 7 halves. And then finally we have our third possibility, which is positive square root of 7 halves, which is actually going to give us the same exact answer if you plug it into the original there. So here's my guess. My guess is either both of these are the closest ones or just this one is. Now, how do we know which one is actually correct? You have to go back to the distance formula problem that we had and actually plug it in. So let's do that. So here's our distance formula problem here. I'm going to plug in all 3 points. I'm going to plug in 0. I'm going to plug in negative square root of 7 halves, and I'm going to plug in positive square root of 7 halves. And we're going to see which one of these gives me the smallest possible output. Now 0 is pretty easy. If I plug in 0 here, these two cancel out. I'm just left with 16, and the square root of 16 is 4. So that one has the point 0, comma, what did we say thing was? I think it was 7. This point is 4 units away from the parabola. Okay. I'm sorry. This point is 4 units away from that point. And this point is actually on the parabola. Now we're going to find out another point on the parabola and see what that one comes out to be. So for this one, we will plug in the negative square root of 7 halves. Okay. So this square is going to cancel the negative and the root. So what I'm going to end up with is 7 times 7 is going to be 49 over 2, not 4. Okay, and then here, the 4 will cancel the negative, and this to the 4th power, well, if you square it, it gets rid of the square, then you square it again and make it a 4th power, you're going to end up with 49 fourths. And then from here, we'll get a common denominator and see what we get. I think for our purposes, I'm just going to go ahead and use a calculator and do decimals and kind of avoid the whole fraction issue going on here. This one comes out to be 1.93. So as you can see, this distance is closer than this distance. And so now this one over here, I can already tell you just by saving you the time, it's also going to be the same. And the reason for that is because we're plugging in the same number, but it's positive. But whether it's positive or negative doesn't matter because we're raising them to even powers. So you're going to get the same thing. So there are actually 2 solutions to this one. So which points on the graph of this are closest to this? Our answers were negative 7 root 2, and when we plug that in for y, I believe we got 7 halves. And the counterpart, the positive version of it, like that. So there's our final answer. I think 2 things I'd really like to draw your guys' attention to is, first of all, how do you set this up? It's a distance formula, so you want to know your distance formula. The other thing is whenever I took the, when I was taking the derivative, I only took the derivative of the inside to make my life a little bit easier. Those are 2 strategies I think I'd really like to stick out to you. There's a lot of other stuff going on here, but those 2 are kind of the big ones to stand out. Okay, so go ahead and take a moment, pause the video, read this. I would encourage you to do the following before you watch me do it. I mean, it's up to you. But I would say, see if you could draw a picture and come up with a primary formula. Okay. So if I were doing this, if we're talking about a box-shaped aquarium, right? So here's our picture. It's open on the top, which means there's nothing up here, right? And they're giving us the volume here. Again, they want to know what dimensions we should use to create an acceptable aquarium with the least amount of glass. They tell us the bottom is a square. Now, if the bottom is a square, that means the length and the width are the same. We do not know what the height is, though. The height would be different from the length. So, for a primary equation, you got to remember, we're looking for what we're trying to minimize. We're trying to minimize the amount of glass. Now, that's a sneaky way of saying surface area. That means the area of every face on this box, and not including the top, because there is no top, right? So the area of this shape on the side here is x times y, right? So the side of the aquarium has an area of x times y, but there's 4 sides like that. So it's 4xy. And then we have the base of the aquarium, which also would require some glass. The base is a square that's x by x, so that's x squared. So we have the 4 vertical sides of the tank and the base giving us the total surface area, which is the amount of glass that would be needed. So that's the primary one. That's the one I'm trying to minimize. I want to use the least amount of glass. Now, the secondary one is going to be the volume. They're telling us the volume right here. Okay, volume is length times width times height, right? We saw that earlier today. They give us the volume. The volume is 1372. The length and width are both x, and then the height is y. So that's going to be x squared y. Okay, so there's my secondary equation. So what you want to do is get one of these variables by itself. I think getting the y by itself would be easier, so I'm going to go ahead and divide both sides by x squared. And then what I'm going to do is I'm going to come up here to this primary and replace the y with what I got there. So what would I get if I did that? Let's see. Right? So let's go ahead and simplify this. First of all, this x will cancel one of these x's on the bottom. And then we also need to do 4 times 1372, which is 5488 over x. Now we want to, that's our primary equation, simplified, and we're going to go ahead and find the derivative. Before I find the derivative, I might want to consider rewriting it like this so we can apply the power rule. So this is going to end up being negative 5488 over x squared plus 2x. And we want that to equal 0, right? All right. Now we can also find where it's undefined, but that's at 0. And so I'm not going to bother with that because the x, remember, represents the base of our aquarium. It wouldn't make sense to have the base be 0 units long. So I'm not going to worry about that particular value. That's not going to give us any meaningful result. So I'm just going to go ahead and find where this thing equals 0. move the 2x to the other side, divide both sides by a -2, get 2744 over x squared equals x. Multiply both sides by x squared, and then take the cube root. Which is 14. So x is 14, and if you want to, and we only got one answer, so that has to be it. If you go back to your secondary equation, our secondary equation was 1372 equals x squared times y. Put your 14 in there and solve for y, you'll get your answer there. Seven. So those are the dimensions of the tank that would help us use the least amount of glass. And they are asking about the dimensions. They're not asking for the actual surface area, so we can just leave it as x and y. All right, so there's that one. Let's do another one. So let's do one like this. Go ahead and read the problem. Kind of sketch what you think that might look like. Now we have a rectangle inscribed inside of an ellipse. So we have an ellipse, and then we have a rectangle that's drawn inside of it. Matter of fact, I think I'm going to draw mine even bigger so that we can kind of see what's going on a little more clearly. So we have an ellipse. It probably doesn't look like this if we actually graphed it, but I don't think we really need to worry too much about the specifics. But we have an ellipse with a graph there. Now they want to know what's the area of the largest possible rectangle that we can draw. So the primary equation is we're looking for the area of a rectangle, right? All right, so every point on here is like over x and up y, right? Over here is left x and up y. This is left x and down y, and so on, right? So basically, you guys can see that the length of this rectangle is 2x and the height is 2y. So the area, which is what we're trying to minimize, is 2x times 2y, which is 4xy. Now our secondary equation is what's limiting the size of our rectangle. Well, it's the ellipse. So this is our secondary equation. Okay, so we need to get a variable by itself. I think in this particular equation it would be easier to get the x by itself. So I would minus 4y squared on both sides. And then I would take the square root. Now you do technically get a plus and a minus, but I think that's just because of the symmetry here of our shape. The positive represents the right half of our graph and the negative represents the left. But if I just solve for x, then I can kind of use symmetry to figure out what the other x values are going to be, right? So I don't think we need to worry about plus and minus there. So now we go back to our original primary equation and we replace the x with what we just found. The x is 25 minus 4y squared, and then we have a y. I'm going to rewrite this though, so it's the 4y is in the front. Now, you could find the derivative of this using the product rule, but I'm going to show you a little trick that we can do to kind of make this a little bit easier. Do you guys agree that 4y is the same thing as the square root of 16y squared? Yes, Mr. Bailey, we do. Okay, good. Well, now since they're both square roots, what I can do is I can actually multiply this 16y squared inside and turn it into just a square root. Okay, so I can do 16y squared times 25. Let's see what that comes out to be. That would be 400y squared. And then 16y squared times negative 4y, which would be negative 64y to the fourth. So the benefit of doing that is that now I've got this as one square root. I don't really need to worry about finding the derivative of the square root function. I can just find the derivative of the inside itself. So we'll call this a sub 1. Where we just look at the inside part. And then I'm going to find the derivative of a sub 1 and set it equal to 0. That's going to be 800y minus 100 and what would that be? 256, I think. X cubed. And then we solve for, wait a minute, shouldn't be an x, it's a y. Let me fix that. There we go. All right, let's go ahead and take out a y there. Probably take out more than that. But I'm just going to leave it like that. So we can see that one of our values is y equals 0. Now that one's not going to be our answer. We want to find the largest rectangle. And if you think about it, if the y was equal to 0, then there would be no height to the rectangle at all, and therefore we would have no rectangle. So we probably won't have that one. Let's go ahead and, I shouldn't say probably, we won't use that one. How's that? Now we're going to set the other part equal to 0. Add the 256 to the other side. Divide both sides. I think I'm going to get away from using fractions. I'm just going to go ahead and use my calculator and start getting some decimals here. So if I divide 800 by 256, I get 3.125. And then if I square root that, I get 1.76. I guess I'll round it up to 8. And there's our y value. Once again, you could get a positive or a negative there, and that's fine, because when we drew the picture, you know, you do get positive and negative y's. You're going to get a point up here, down here, up here, and down here. So it doesn't really matter. What was the question asking us? What was the area? Okay, so that was the y value, right? Let's go ahead and find our x value now. So you take your y value and you plug it into your primary, right? So let's keep this. We're going to want to remember that number. Now let's find our x value. So we have x squared plus 4 times my y value squared. So that's going to be 5. It's not equals y, you guys. Mr. Bailey needs to get his stuff straight. Minus 12.5 on both sides. And then take the square root of that. And get 3.536. So in the world of decimals, this is what the x and y values would be. But remember, they're actually asking us to find the area of the rectangle. Okay, so what I've just found is the coordinates. This x value is 3. I'm going to redraw it so it's a little bit bigger. Let me write out my x and y values here a little bit. Okay, so I've kept my y values up there at the top. I've got them written over here. So now they want the area of this rectangle. So the area of the rectangle is basically going to be whatever this x value is times 2 and whatever this y value is times 2, because this y value is doubled this way and this x value is doubled this way. Now we had our original area function. I believe we had 4xy. So if we just plug in these x values and y values, we can get our final answer here, 3.536, and I'm going to put the other one underneath because I'm out of space. But we're multiplying all three of those together. So let's go ahead and do that. Getting about 25 is my final answer. Okay, so that's probably going to be the last one I'm going to share with you guys today. There are a variety of other kinds of problems. I think you guys can kind of look at them on your homework, and I would challenge you to try some of the ones that I haven't already done examples for, but I've covered quite a few of them. But anyway, enjoy your Wednesday off, and we'll see you guys on Thursday.